Hi, in this video, we want to look at the concept of elasticity. During the course of this video, we'll be looking at the meaning of elasticity, we'll try to define what it means when a material is said to be elastic in nature. We'll also look at the law that governs elasticity, where we state the meaning and the implication of Hooke's law. Then also we'll talk about terms that are associated with elasticity. So from verification of Hooke's law, we arrive at terms like proportionality limit, elastic limit, the yield point, the breaking point, ultimate stress, strain, mass stress, and the ratio of the stress and strain we've mentioned, and so on and so forth. Then we move on to looking at how to calculate work done by a stretch spring or work done in a stretch spring. And lastly, we talk about potential energy or elastic potential energy. All right, so what does elasticity mean, or what is the meaning of elasticity? Now, I want you to picture a rubber band. Why I say this, a rubber band, by the time you apply a force to it, if you stretch it, what happens? And then you remove the rubber band from your hand. Let's say, for instance, you have a rubber band like this, and then you apply a force in this direction, apply another force in this direction. Now, what happens when you remove these forces? You see that this rubber band goes back or snaps back to its original size or shape. Now, how does that relate with elasticity? So we say elasticity is simply the ability of a material or a substance to regain its original size or shape. The ability of a material to regain its original size or shape when it has been distorted by an external force. Remember our rubber band there, what do we apply? You take your hand, you're applying the force maybe towards the right, you're applying another force towards the left. So what happens to this rubber band? The size, increases. But what happens when I remove my hand from the rubber? You see that it snaps back to its original position. So that's why we define elasticity as simply the ability of a material or a substance to regain its original shape or size when it has been distorted by an external force. All right. Now, let's say we have a material. Let's say we have a material like this, and then this is my material. So initially, my material has a length. So let me see the length of my material. Let's give it to be L naught. Write this as L naught. So that's the initial length of my material. Now, what will happen when I decide to place some form of load on this material? Now, remember the principle of the rubber band. So by the time you apply a force on it, what happens? It stretches. So same thing will happen here. So if this is my material and then I attach, let's say, a load in form of a mass to it, now this material will stretch. Now we have a new length of this material. So let me say from this point to this point, my length here is LF. That is the final length. What we're saying is after I've applied this load, let me write M here. So after I've applied this load M in this material's length or this material's size or this material's shape is going to increase by a factor of delta L. Now, when this happens, now peradventure I now remove this load, I remove this mass M. If it go back to its original position or shape or its size, then definitely I can say that this material is elastic in nature. So that's what elasticity is trying to tell us. Now, it's not always every time that the material will be hanging, like the load you're applying will be hanging like this. Of course, we know that the force this material is actually experiencing is as a result of the weight of this object here. So let's say, for instance, maybe we have a material that is placed horizontal now. So for this one, let's use the concept of our string. So let's say I have a string like this. So that has an original length. So this is the length of my string. from this point to this point. Let me call it again. Let me call it L naught. Okay. Now what happens when let's say for instance, I apply a force. Think of this like the rubber band example. So I decide to apply a force to stretch this spring like this, and see that my new length now is from this point here up until this point. So let me call my new length L phi now. Okay. Now, once I remove my hand from this string, I'm applying a force in this direction. Once I remove my hand from this string, what do you think will happen? What do you think will happen? This material snaps back to its original location, like this position we are seeing. Sorry, so that's okay. So that is this position we are seeing here. So I can say, okay, from this point to where this point is, it should be my change in length. So whichever analogy you feel comfortable with, even if it is that rubber band scenario, so that's also great, just to understand the concept of elasticity. Now, for the law that governs elasticity, first I'm going to write the equation. So we have two equations practically. So the first one, F is equal to K change in L. So let me write this as FA, applied force. And this second one, Fs is equal to minus K change in L. All right. So what does FA means? What does Fs means? FA simply refers to the applied force. If I'm applying the force, on this spring, right, the force I'm applying is going towards the right, right like this. And then the extension, the change in length, is also moving towards the right. You can see FA towards the right, extension X or L, since we're using L here, so extension L is also moving towards the right. So when this happens, and then we say Hooke's law is obeyed, we can see FA is equal to K change in L. But for this other equation, now, this other equation, we mostly use it in simple harmonic motion. So I won't talk much about this, but I'll just say what it meant or its implication. Now, let's look at my spring, for instance, or the rubber band. By the time I take a force, and then I use that force to stretch this spring to this distance. Now, once I release this, what's it called? Once I release the spring from my hand, this spring tends to what? Go back to its original position. Of course, when it is going back, it compresses first, stretches again, compresses, stretches, compresses, stretches. If friction is in place, then at a point in time, we'll notice that my spring or this spring goes back to the exact position it has started with. But let's just imagine that after releasing this string here, it went back directly exactly to its equilibrium point. Now, the force that will be responsible for making the object move will be the restoring force, or Fs, the force of the spring. Remember, you take the rubber band, you stretch it. By the time you remove your hand, it goes back to its original length. So that means it has built up enough potential energy to want to go back to its original length, hence the negative sign. Now, when you are reading your textbooks, if you see this particular formula there, and then you don't see this first one, don't be alarmed. FA and Fs are equal in magnitude. Fs is just in the other direction, while Fa, the applied force, is in the direction of the displacement that you are having initially. So I hope this makes sense. All right. Now, these two equations I've written is gotten from Hooke's law. The two equations I've written is gotten from Hooke's law. So Hooke's law is simply telling us that the force that we apply uh, is directly proportional to the change in length or the increase in length, provided the proportionality limit hasn't been exceeded. I repeat myself, this force that is applied, whether in form of Fa, of X, or Fx, will be directly proportional to the change in length, directly proportional to the change in length. That is, if I keep on increasing the force, the change in length also will what? Would also be increasing. So provided the proportionality limit has not been exceeded. So what happens when the proportionality limit is exceeded? Then Hooke's law is no longer true, or we say Hooke's law is no longer obeyed in that particular scenario. I guess the best way to explain Hooke's law is to try to draw a graph of force versus extension. So when we have that, then we can definitely see what is actually going on. All right. Now let's say we have a graph. This is my graph of F. So F on the vertical, and then change in L, or L on the what's it called? L on the horizontal. Now, what we're simply saying is, imagine my rubber band. So let's say my rubber band initially has a size of 2 meters. Now, if I keep on applying, if I apply, let's say I apply 1 Newton force, and then this rubber band is able to move 0.2 meters, is able to stretch. Now, what Hooke's law is telling us is, if I keep on increasing this force, so let's say I double the force, 2 Newton, this one will increase in the same proportion. So if this is 0.2, what happens when I increase the force to 2 newtons? So again, this one moves by, so this has moved by 1, so this also will move by 0.3 meters. So again, let's say I increase it by another 1, so 3 newton. Again, this increases by 0. What's it called? 4 meters. So as I keep on increasing and increasing and increasing, this change in length also keeps on increasing, in as much as I'm still in the proportionality limit. Let's let's say we've exceeded the proportionality limit, and then I decide to apply let's say force of 4 Newton, and then we're no longer in the proportionality limit. Then my extension, instead of it, this is 0.4, instead of this to be 0.5, I might be having maybe like 0.45. It won't be exactly in the same proportion. Of course, the material still has some form of elasticity, but then proportionality limit has been exceeded. So as I'm increasing one, the other is not increasing by that factor. It might be increasing by more or by less, but it won't exactly be equal. So if I increase this by 6 Newton, this might just be, let's say, 0.5 or 0.51 or 0.49. It doesn't, that is what Hooke's law is trying to tell us. But what if we now exceed the elastic region? Then definitely my material now tends to behave like a plastic. So let's try and represent this on our graph. So let's say we have a graph of F against L. So initially, I have a linear graph that looks like this. Then after some point, you see that my graph tends to start curving, and then I have a final point at this region. So let me call this point here, the origin, let me call it A. Let's call this region where my graph is straight, let's call this B. Let me call this point C. Let me call this point C. Let me call this point D. And then let me call this point E. All right. So A to B, point A to B, we can refer to it as the proportionality limit. Proportionality limit or region. Limit or region. So you can see that from A to B, this graph is behaving like a straight line. So as F is increasing, L is also increasing by the same proportion. So that's from A to B. Now from A to C, we say it is the elastic limit. Elastic limit. Remember, we defined elasticity as the ability of a material to go back to its original shape or size when it has been distorted by an external force. So from A to C, of course, Hooke's law is no longer obeyed from B to C, but from A to B, Hooke's law is obeyed. That's why we have the F is equal to K change in L. But from B to C is still an elastic limit. So it means that if I keep on stretching this force up until this point, by the time I release my hand, it still goes back to its original shape or its original size. How about from C to D? From C to D, now if I apply any force that is greater than this point, what happens to my what's it called? What happens to my material? My material would now lose all its form of elasticity. That is, by the time I release my hand, it will never go back to its original position. So let's assume that, remember this rubber band, we started with 2 meters. By the time I stretch this beyond point C, now when I release my hand, of course, it goes back to some size, but the size will never be equal to 2 meters. Let's say it goes back to 2.5 meters or 3 meters or even 4 what's it called 4 meters. So the point is, by the time you release your hand from the rubber band, instead of going directly to 2 meters, it is now going to something higher than what its original started from. That's because it has been stretched to its plastic region. Then from point D to E, my material doesn't have any form of elasticity again. So now it's now behaves like a pure plastic. Shake like a pure plastic or a thread that doesn't have any form of elasticity. So if you keep on stretching, so let's assume that you now stretch the material to 6 meters. By the time you release your hand, the length that it goes back to will also be equal to 6 meters. It doesn't change in size any longer. Then point A is the maximum elongation the material can have. You can see that from the graph. Let's try to calibrate this graph. Let's say this is 1 meters, this is 2, let's say this is 3, this is 4, this is 5, this is 6, this is 7. So from the material, anything that passes any force you apply beyond this point here will break the material. You can see a rubber band, by the time you stretch it too much, what happens? It cuts. So any force or the maximum force you can apply to a material without it breaking will result to its maximum elongation or the maximum length the material can have. And the force you're applying to this material to bring it to this point, we call it the maximum force, F max, or the ultimate strength of said material. I hope this concept makes perfect sense. All right, now that we've talked about this, then let's talk about some other terms that we've been talking about during the course of our graph. So we want to talk about the meaning of stress. Stress. Well, what does it mean when we say a material is undergoing stress? Remember the example we cited earlier from the beginning? We said we have a material like this, and then we're applying some form of load in form of a mass to this material. So what happens? In as much as this material, the initial length is L naught, and this one here is LF. So this material has undergone some form of stress. Now the type of stress this material has undergone, because you can see that the final length is greater than the original length. You can see that the stress this undergo can be classified as the tensile stress. Now we have different type of stress. We have the tensile stress. We have the bulk stress. Especially terms that we associate with all these civil engineering courses. But for the sake of this subject, we only deal with tensile stress and compressive stress. So for tensile, the final length has to be greater than the original length. So what it particularly means is the material is actually stressing. So for compressive stress, it means the material is shrinking or we are trying to reduce its size. So how do we calculate for stress? So stress is simply the ratio of the force you're applying. So the force that this mass is given in form of its weight, that is mg. If you know the mass of this object, so let's say the mass of this object is 10 kg, and then we're given the acceleration due to gravity, whether 9.8 or 10 meter per second squared. So multiply that, that will be the force that this material is acting on this particular rod that we've had here. So the tensile stress is simply the ratio of the force that is being applied to the area where the material is feeling the force exactly. So you can just think of this like, let's say, for instance, just trying to draw this picture in the upside down region. So you can see that the mass is applying an upward force. So this region here that it is striking the surface of this metal will feel some form of stress. And the stress it will feel is simply gotten by the force that is being applied divided by the area in which this force is being felt. And stress, the unit for stress is simply the Newton per meter squared. Of course, we're familiar with this unit already from pressure. So definitely, they dimensionally they mean the same thing. But for pressure, of course, we talk about pressure in solid, we also talk about pressure in liquid. But for elasticity, we refer to that pressure as stress. Now, after you've undergone or after you've actually apply a force to this object, and this material is already feeling some form of stress. Now, the evidence of this stress, or the result of this stress that is being felt by this material, now gives rise to another phenomenon referred to as strain. So strain is just like or is just referred to as the evidence that a material has undergone stress. And strain is simply the fractional length the material has gone when it has been stressed. Or you just say the change in length divided by the original length. For length, the unit is meters. For increase in length, rather, the unit is the meters. While for the change in length, the unit is also the meters. So meters cancel out meters. You can find out that the strain is actually dimensionless. So when you're solving for strain and then you're struggling to look at the unit to keep, remember that strain doesn't have any unit at all. All right. Now, what happens when we decide to take the ratio of the stress and strain? So let's say we try to divide them by each other. Then it gives rise to another phenomenon we call the what's it called? The Young modulus. Young modulus or elastic modulus. So in some textbook they represent it with E, some they represent it with U. So let's just use E for this. And E means stress over strain. So stress over strain. So remember, stress is force over area, strain is what? Change in L over L naught. So the unit for stress and the unit for elastic modulus is simply the Newton per meter squared, because strain is dimensionless. So let's try to expound this. Let's say we have E is equal to, what's my stress? F over A divided by strain, means change in L over L naught, and then F over A multiplied by L naught over change in L is equal to E. So what is this telling us? So it's just trying to tell us that the elastic modulus of a particular material is its ability to withstand what's it called? To withstand, or to its ability or the ultimate strength of the material. So you can see that the ultimate strength of the material depends on the force you're applying, depends on the what's it called? The original length of the material. So if the force you're applying is higher, the elastic modulus of the material increases, and if the original length is also higher, the elastic modulus of the material also increases. It's just trying to tell us how a material wants to increase in its size, or doesn't want to increase in its size. What if we decide to make delta L the subject of the formula? Delta L the subject of the formula, what will happen? So here we simply want to cross multiply. So I can say delta L multiplied by E must be equal to F times L naught, isn't it? So since I'm multiplying by these two, everything here, so it must mean that I'm partially dividing this by A, F over A, and then dividing this by E, isn't it? Okay. All right. So now that this is said, um, now that this is said, what does it mean? It means that the change in length of a material. So let's say, for instance, I have this material here, and then I want it to increase. If I want this change in length to increase, the force must be increasing. So the more the force increases, the more the more increase in my change in length. And then the original length too, the higher it is, then the more it can increase. It just simply means, let's say we take two metal of the same property, that is, if this is iron, this also is what? This also is iron. If I apply the same force on these two metals, so let's say I apply a force of 2 Newton on this metal over the same area, this one also 2 Newton on this area. So it means that this force here will increase more, or the change in length here would be higher than the change in length of this one, because change in length actually depends on the force, or is directly proportional to the force rather, and also is directly proportional to the original length. So, and then change in length is inversely proportional to the area. So it means the higher the area, the lesser the change in length, and then the higher the elastic modulus of the object, the lower the change in length of said object. I think we've talked about this before now. So when we're looking at the concept of Hooke's law, F equals to K delta L. So all right, so let's try to make F the subject of the formula here, and then see what we can bring out from this scenario. So if I'm making K the subject of the formula, then it must be, or F the subject of the formula rather, from this equation, then I can say F is the same thing. F is equal to what's it called? E dot A dot delta L, everything over L naught. So E dot A dot delta L, everything over L naught. But remember, Hooke's law is telling us that F here, the applied force, must be equal to K delta L. So it must mean that K here, or the value of K here, is simply this. So K is equal to E A delta L naught. So what does K depends upon? Of course, K here means the stiffness of the spring, how stiff the spring is. So if I'm looking at a very a stiff spring, like the springs we find underneath the is it heavy duty vehicles like the caterpillars, the cranes, and so on and so forth. So before those the force required to stretch those springs, you see that it is extremely high. So if you can see the spring physically, now if you want to try to stretch the spring or compress the spring, it might not be possible unless you use maybe a machine to do so. But look at weaker strings like maybe a guitar string. When you want to stretch it, you see that the force you apply is slightly low, and then once you apply that low force, it's increased by much. So if you want to create a material that will have what's it called, an high elastic nature, then you want to use a low K value, and vice versa. So I hope this concept makes perfect sense. All right, so moving on to the work done in stretching a string. So how do we calculate the work done in stretching a string? Now for work done, we know from work energy and power that work done is simply gotten by taking the product of the force times distance. So work done is equal to what? F times D. Remember? But why we can't rely on this, what's it called? Why we can't rely on this formula for elasticity is that for this one, or when we're taking work energy and power, the force we are applying was constant all through. Remember from the graph we drew, we said if we have force versus displacement. This time around, we are concerned about the proportionality limit alone. So if my force here is 1, the force I'm applying at this point is 2. So if the force is not constant, and then you can see my displacement. Let's assume that this is my maximum displacement here. So let me call it what? L max. So you can see that for this one, since my force is not constant, so what do I simply need to do? Just try to find the area of this shaded, or the area of the shaded part of the proportionality limit. And this shape looks like a triangle. And how do we find the area of the triangle? Simply 1 over 2. Then from this point, if this is 0, this is 0 to this point has to be L, because we're plotting a graph of F against what's it called? Against L. And then from this point to this point still has to be F. So you can say that my base 1 over 2 times base. So my base here is L, and then my what's it called? My height here has to be F. So this is how we calculate work done for work done in stretching a spring. So writing this in our original equation, so since W equals to F times D, then we can say that W is equal to 1 over 2 times L times, now, okay, so sorry, I'm not supposed to write L, I'm supposed to write change in length. So L, then times F that is being applied. But remember, we already said F is equal to what? K change in L. So I can write this formula and say W is equal to 1 over 2 times, so instead of writing F, I want to write it in terms of K change in L. So it becomes K change in L times change in L. So change in L times change in L, what do we have? So that's 1 over 2 times K times change in L squared. So in some textbook, this change in L, they write it as E, or they write it as L, or they write it as X. But be careful, the X, the E means change in length. So it's better you write it like this, so that when you're solving any question, you'll be able to know what exactly to use. So lastly, let's move on to the elastic potential energy. Elastic potential energy. Elastic potential energy. Now, from work energy and power, we're told we have different types of energy. We have the kinetic energy, we have the potential energy, we have the chemical energy, electrical energy, and so on and so forth. Then for the potential energy, we're told we have multiple types. So there's a reason why if you throw an object up, the object will fall down. That's as a result of its elastic gravitational. I say elastic. That's as a result of its potential gravitational energy. But for that of a spring, there's a reason why when you stretch a spring to its maximum elongation that it can take, and then when you release it, it snaps back to its initial position. That's because it has built enough potential energy, and then the potential energy allows it to snap back to where it wants to be. So how do we now calculate that or such potential energy? We need to know this formula: work done being equal to the change in potential energy. So work done equals to the change in potential energy. And what does change means? The change must mean potential energy final minus potential energy initial. So remember our formula for work done. We say work done is 1 over 2 K delta L squared, isn't it? So if I were to expand this must mean I have 1 over 2 K delta L final squared minus 1 over 2 K delta L initial, okay, squared must be equal to potential energy final minus potential energy initial. So from here, I can just equate the equations together. So I can say potential energy must simply be equal to 1 over 2. Now, sorry about this. This shouldn't be delta L final. It should be L final rather. Should be L final. So let me just quickly make that adjustment. All right, so this should be KL final squared instead, and then KL initial squared. So potential energy will now be equal to 1 over 2 KL squared. So whether we're talking about the final point or the initial point, or at any point in time in the spring stretching. We'll have come across this formula again. We've treated SHM. So this is where we got it from.